Hey, what's up, guys? So welcome to my Lebesgue major theory video. So today let's prove the main three theorem in the Lebesgue major theory. Basically, it's all the important theorem comes from these three. So the first one is a monotone Lebesgue monotone Lebesgue monotone convergence theorem. And the second is the also famous Fatou's lemma. And the third is the most famous, the monotone. So basically, the back dominates convergence theory. The back dominates convergence theory. Okay, so these three are most commonly used. So usually key step proof. So the proof start from 1, proof 2, to proof 3. Okay, so before I start, I hope you guys subscribe to my channel. Okay, and if you haven't seen my previous video about the basic major theory and the basic technique we need to use, then you can go to see this. Okay. Yeah, so let me just quickly introduce notation. So when I say F is LU, or basically U is usually now recording as the Lebesgue measure, and what it means that the absolute as said, if I say F is LU on E, means that the absolute value means that the absolute value of function F integral on E, which is finite. Okay, so basically this is my definition. Okay, so yeah, so now let's go to proof 1, which is the monotone convergence. Okay, and also let me just introduce. So when I say E belongs to this, means that E is a Lebesgue measurable set. Okay, so F is a measurable function. Notice that the measurable function and the F belongs to LU on E are different. When I say F is measurable, I mean by definition, this X, F of X greater than A, which is a measurable set. But when I say F is LU on E, means that F integral on E is finite. Okay, so let's quickly prove the first one, which is monotone. So settings that E is, belongs to some measurable set, and the set Fn is a sequence of measurable function, which is non-negative. So Fn is a sequence of function, basically which is monotone increasing. So basically what I'm just saying is this. Okay, and for all x belongs to E, and one can define the F to be, let's say, limit, right, n goes to infinity, f of n. So basically, or somebody like to write f of n approach f piecewisely. And so basically, your results start from here and here. So basically, you need to assume that this f exists. Then this is called monotone convergence, means that the limit and the integral can exchange. So basically, this guy. By the way, this is sorry, I need to mention that this Fn is measurable. So this makes sense. And Fn et mu, when you take n to be infinity, will be the same as this. Okay. Okay, so this is called the monotone convergence. Okay, so let's see the proof. Okay. So let's introduce, let's say, let's define this guy as n goes to infinity, approach to convergent to some alpha. Okay, belongs to a real number. Obviously, that if the alpha is infinity, then you can prove that. I mean, if alpha is infinity, then both of them will be infinity. So we can further assume that alpha is finite. And then let's say take n to be, and then we know the fn is increasing, right? So basically, if you take limit n to be infinity from both sides, which you obviously prove that alpha is less or equal to f d mu e. This is almost trivial, right? Because this f of n less or equal to f. So you get f of n d mu e less or equal to f d mu e. And you take n to be infinity, then this become alpha, right? So alpha less or equal to this. So this is one direction, and we hope to prove that another direction is correct. So this direction is almost follow trivial. Okay, so another direction, very strange. Let's say choose c to be less than 1 and greater than 0. And by definition, let's choose some simple function s, which is less or equal to f. So now I want to use the property of the definition of the back measure, and I define en, which is x, such that f of x greater than c times s of x. Okay, and notice that the E1 subset of E2 is a subset of E3. Keep going, and one can prove that E. Let me just define E. So I define. Sorry, not define. Okay, so you can prove that E is a union of En. E is this original set E, right? So basically, your E1 basically is F1 greater than or equal to CS X, and E2, right? But you know that F1 is increasing, right? So E1 less or equal to up to infinity. Okay. And obviously that E will be least because when n goes to infinity, then Fn is can approximate approach F, where by definition your S less or equal to F. So finally, this E will every point will satisfy the property by my definition. Okay, and okay, so now yeah, so let me for every n, our Fn d mu E greater than or equal to Fn d mu En, okay, which greater than or equal to C S d mu En. So we have this. This part trivial because En is a subset, and also this part is trivial because Fn greater than or equal to Cs on the En. Okay, so let's take n to be infinity. So if I take n to be infinity, the left-hand side becomes alpha, which alpha greater than or equal to Cs d mu En. So now I take another time which n goes to infinity, which become, let me see, right? So if I take n to be infinity for this side, I get this. If I take n to be infinity on this side again, I get alpha less or equal to C times become what? Become S d mu E. And I take sup. So take sup. So I prove that alpha greater than or equal to so now I can also approach. Okay, so let me just do step by step. So up here, I first take C to approach to 1. Okay, because this works for any C. So C approach to 1, which I prove this for every S. Okay, so now proof is clear, right? Because I can take the suprema of S and by definition, this is the Lebesgue measure. So we prove that alpha greater or equal to F d mu E. Okay, so this and then combined with the previous this one, which we prove that the F d mu E is limit and goes to infinity, Fn d mu E. Woo! Nice shot. Okay, so this is the monotone convergence. Okay, and okay. So let's see. So yeah, there's a simple corollary. So let's write as theorem. So this is the, let's say E is the back measurable set, and let's say Fn is non-negative function. And if you define F to be summation of Fn, which earn from, let's say 1 to infinity. Suppose converge, okay? Then your f d mu e will the same as take the n equals to 1 from infinity, fn d mu e. And the proof just basing, so the proof is just one line using monotone convergence. On what? On partial sum, right? So you can define, let's say gk, which is fn from 1 to k. So obviously that gk is an increasing function, and fn is measurable, so their summation is measurable. Oh, by the way, you can prove that let's say you can prove that if f1 and f2, if you can prove that if f1 and f2 are both measurable, sorry, f1 and L2 belongs to this LU, then f1 plus L2 belongs to LU. A very simple exercise also using the monotone convergence. Yeah, or basically follow your definition, right? Because two simple function addition will be simple. I mean, you can try to prove, not very difficult. Okay, so yeah, this is the proof. Yeah, so let's prove the second, which is a Fatou's lemma. Okay, how about let me just change your color. Okay, so let's define f of x to be limit inf. So remember the limit inf is, okay, I will remind you guys what is in limit inf. Okay, so let's say fn is also a non-negative function. And suppose that it limit inf of fn, right? I call it f. Then, so Fatou's lemma says this. So basically, if you take limit inf outside the integral, which will greater than equal to the limit inf take inside. Okay, and these guys proof can be easily used using the monotone convergence. So let's write down the proof. Okay, so proof. Let's define gk, which is a function which is infiniment of let's say fk of x at gkx and the k greater than equal to n. Okay, so obviously that if you increase, sorry, this is gn. So if you increase n, right? If you increase n, then infiniment will start to increase, right? So you have g1 less or equal to g2, okay. And obviously that for each n, right? By definition, this is infiniment. So this is the first one we have. The second one we have is gn less or equal to fn, because gn is an infiniment of fn. Okay, so first we notice that since fn is measurable, okay, by the way, so I forgot. So fn is greater or equal to 0, and definitely fn need to be measurable. Yeah, our measurable function. So basically all we need in all videos for the back theory, everything need to be measurable. Okay. Let's see. Okay, so we know that f is measurable by the previous I think I previously proved that if f is measurable, then f will be measured. Okay, so now yeah, so now notice that let's say write f into, right, this is a definition. So limit inf definition is the limit of this g. Is a limit of this g. So you can write this as this. This is just a limit. You can interpret that this is the definition of the limit inf. Okay, so this is the first step. Okay, so now second step is that let's do the integral, which is a limit, right? So this is limit of gn, right? Now this proof looks stupid, right? So, and then by the monotone convergence, so now I can apply the monotone convergence, because this guy is monotone, right? So this is limit n goes to infinity, gn d mu. Okay, so now which is less or equal to limit n goes to infinity, because each term is less or equal to fn. So this guy okay, so now we have this, right? Now we can do what? we just change limit into limit inf. Okay. Because if the limit exists, so this guy will less or equal to can be changed as a limit inf. Right, so this is just fn d mu e. Right. So f less or equal to limit. Okay. Yeah. This is the dominant convergence theorem. Okay. Okay, and the dominant convergence theorem has some. Sorry, this is the Factau's lemma. I'm not stupid. I'm stupid. Yeah, this is Factau's lemma. Okay, so now the final is what? The final is the Lebesgue, the famous one, which is called Lebesgue dominant convergence theorem. Some people call it LDCT. This guy is the most important one, the most powerful one. Okay, because somehow usually your function will not be monotone. So sometimes monotone is hard to achieve, right? But the Lebesgue's dominant convergence will say that if your function is universally bounded, then I can exchange the limit with the integral. Okay, so same setting. Let's say E is some measurable set. And the Fn is a measurable function. Okay, so notice that now I don't require Fn to be non-negative. Remember in Fatou lemma, the non-negativity is really important because we need to use the monotone convergence. And so suppose there exists G, which is integral is finite on E, which cover all the F. Let's say G of X. Then, so this is called dominant, right? Because this Fn for every n is dominated by some universal function G. Then this integral you can exchange with the limit. This is the back dominant. Okay, so the proof is very, very interesting. Okay, so the proof is that so I know that Fn is dominated by G. So that means what? That means Fn plus G is greater or equal to 0 for every n, right? So which tell you that you can use the Factau's lemma. So using Factau's. This is the first time I use Factau's. So E, which Fn plus G, this integration plus the limit inf and goes to infinity will greater than F plus G. Because I take n to be infinity, this guy become F. Okay, but now G d mu is finite, right? So G d mu finite, so that I can get limit inf and goes to infinity Fn d mu. I can cancel with this. I can cancel with this G. Okay, so I proved that the limit inf Fn greater or equal to E F d mu. So this is just Factau's lemma. But since it's positive, so I can use Factau's lemma, and this G d mu is finite, so I can cancel out. So this is a very beautiful step. Okay, and let's say the second step. So second step is also let's say, right? So your Fn is bounded by G. So which say that G minus Fn is also greater than 0. So G minus Fn is greater than 0. So you can use what? You can use a second time Factau's lemma. So you get Gf d mu. So this is Factau's lemma greater or equal to limit inf and goes to infinity. G minus Fn d mu E. Okay, so now G is also finite. So you get minus F d mu E greater than equals to limit inf and goes to infinity. Fn d mu E minus. Okay, so when you times minus, then limit inf become limit sup. So which you prove that the limit sup n goes to infinity. Fn d mu E is less or equal to F d mu E. Okay, so now F d mu E is greater than some limit sup, but less than some limit inf, right? Which is nonsense. The only way to make these holds is that limit inf of this f and d mu the same as the limit sup. Right? Otherwise, that this guy, if this guy is not different, it's different, then there's no way that the previous two equation holds. And definitely there will be what? There will be our f d mu. Okay, so very, very beautiful. The proof is so so beautiful that you start from monotone and the Fatou and dominate. This is very beautiful theorem. Okay, and let me just say a corollary. So this corollary may be sometimes used. So if your set, which is a measurable and a finite volume, which Fn and your Fn is universally bounded, then when Fn approach F, then you can exchange the integral and you can exchange the integral with the limit. And then the proof is just the back dominant. So LDCT, but I choose G to be M. So you need to prove that G integrate on E is finite, right? But this is trivial, right? Because this E, the mu will be M just mu E, which are finite. Okay, so in a previously we need uniform convergence to make the limit and the integral can exchange. Right, but now we have LDCT, so we are more powerful than the previous. And LDCT are powerful language that you can use. I think there are many other real analysis theorem can be proved by using this technique. Okay, and the next time I'm going to talk about the comparison with the Riemann integral and the Lebesgue integral. So somehow connecting the Riemann integral definition and the Lebesgue integral definition. And I talk about some theory in the complex analysis and the so-called L2 functions. And we finish the Rudin's analysis idea. Then I will go back to our topic. And after maybe a few months, I will go back to restart a Zigama approach for the major theory. I want to talk about more advanced things. Subscribe to my channel. Hope you guys good luck.